In 2011, Adam Riess won the Nobel Prize for proving the universe is accelerating apart. He thought the hardest question had been answered. He was wrong. Years later, standing in front of the most precise data ever collected, Riess delivered a warning that unsettled the entire field of cosmology. Two methods for measuring how fast the universe expands should agree. They do not. One reads the infant universe and predicts a number. The other measures the universe today and gets a different one. The gap between them has been growing for over a decade. James Webb was supposed to close it. Instead, it confirmed that the gap is real. And what that means for our understanding of reality is far more disturbing than any single strange object floating in the dark. If you find this kind of deep science fascinating, a like and a subscribe go a long way. It helps us keep making these videos, and it tells us you want more of the real stuff, the kind that actually makes you think. Are you comfortable? Let's begin. Most Nobel laureates slow down after the prize. Adam Riess did the opposite. The discovery of dark energy, the invisible force pushing the universe apart at an accelerating rate, had earned him the highest honor in science. But it had also opened a door onto a deeper problem, one that had been eating at him for years, a problem that would eventually become more unsettling than the discovery that earned him the prize. He wanted to know exactly how fast the universe is expanding right now. Not approximately, not within a loose range. He wanted a number so precise that there was no room left for doubt. He spent the next 2 decades building that number. His team is called SH0ES, an acronym that stands for supernova H0, for the equation of state of dark energy. The name sounds technical, but the mission is simple. Measure the current expansion rate of the universe to 1% accuracy. Lock it down. Remove every source of error. Make the measurement so clean that no one can argue with it. By 2022, he had done it. 30 years of Hubble Space Telescope observations, more than 40 galaxies, over 1,000 individual Cepheid variable stars measured one by one, cross-checks against geometric anchors, against different types of stellar distance indicators, against every calibration method available. The result was approximately 73 kilometers per second per megaparsec. That number means this. For every megaparsec of distance you look outward from Earth, approximately 3.26 million light-years, the universe is stretching space at an additional 73 kilometers per second. The further out you look, the faster everything appears to be receding, not because objects are moving through space, but because space itself is growing. Every point pulling away from every other point as the fabric of the cosmos inflates. 73, a hard number built on decades of careful work. It should have been the end of the story. It was not, because another group of scientists, using completely different data from a completely different era of cosmic history, had their own number, and their number was not 73. It was not 71, it was not even 69. It was approximately 67, and they were just as confident. That is where the trouble started. To understand why a gap of roughly 5 or 6 units between two measurements could threaten to unravel our understanding of the universe, the expansion rate of the universe is described by a single value called the Hubble constant. It is named after Edwin Hubble, the American astronomer who first demonstrated in 1929 that the universe is expanding at all. Before Hubble, the dominant view among scientists was that the cosmos was static. Stars moved, planets orbited, galaxies drifted, but the universe itself, the stage on which all of this happened, was fixed. It had always been roughly the size it is now, and always would be. Albert Einstein himself believed this so strongly that he added a term to his equations of general relativity, specifically to keep the universe from collapsing under its own gravity. He called it the cosmological constant. It was a mathematical patch designed to hold the universe still. Then Hubble sat down at the 100-inch telescope at Mount Wilson Observatory in California and looked at galaxies. What he found changed everything. Nearly every galaxy he observed was moving away from us, and the further away a galaxy was, the faster it was receding. This was not random motion. It was a pattern, a direct, linear relationship between distance and velocity. Double the distance, double the recession speed, triple it, triple it. The only way to explain that pattern was to conclude that space itself was expanding. Not that galaxies were flying apart through a fixed container, but that the container was growing, carrying everything with it. Hubble published his result and attached a number to it, a rate. How fast this expansion was occurring per unit of distance, that number became the Hubble constant. And almost immediately, it became one of the most important quantities in all of science. Because the Hubble constant is not just a speed measurement, it is a key that unlocks the age of the universe. If you know how fast space is expanding now, and you know how that rate has changed over time, you can run the clock backward and calculate when the expansion began. That moment, roughly 13.8 billion years ago, is what we call the Big Bang. Change the Hubble constant and you change the age. You change the size of the observable universe. You change how much dark energy there must be. You change the predicted fate of everything that exists. One number, and the entire cosmic picture shifts. The problem that plagued astronomers for the rest of the 20th century was that nobody could agree on what the number actually was. Hubble's original estimate was wildly off by modern standards. He calculated a value that implied the universe was only about 2 billion years old, which was embarrassing because geologists had already proven that rocks on Earth were older than that. The universe cannot be younger than its own contents. That contradiction was not a minor footnote. It was a full-blown embarrassment for the young science of cosmology. Geologists had radioactive dating. They could measure the age of rocks with confidence, and the rocks said Earth was at least 3 billion years old, probably closer to 4.5. If Hubble's expansion rate was right, the universe had to be younger than the planet sitting inside it. The mathematics did not allow both to be true. For decades, the problem festered. Different astronomers using different techniques arrived at wildly different values for the Hubble constant. By the 1970s, the field had split into two hostile camps. On one side was Alan Sandage, Hubble's intellectual successor at the Mount Wilson and Palomar observatories, who favored a value around 50. On the other was Gérard de Vaucouleurs, a French-born astronomer working in Texas, who argued for a value near 100. The difference was not a minor academic quibble. A Hubble constant of 50 implied a universe roughly 20 billion years old. A value of 100 implied a universe of roughly 10 billion years, uncomfortably close to the ages of the oldest known stars. The two camps published competing results for years, each questioning the other's calibrations, dust corrections, and choice of distance indicators. Conferences became battlegrounds. Careers were defined by which side you took. The Hubble constant wars, as they came to be called, were among the most bitter scientific disputes of the 20th century. The war was not resolved by argument. It was resolved by a telescope. In 1990, NASA launched the Hubble Space Telescope into orbit above the blurring effects of Earth's atmosphere. One of its primary scientific missions, designated the Key Project, was to measure the Hubble constant with enough precision to end the debate. The project was led by Wendy Friedman, a young astronomer who would go on to become one of the most influential figures in the field. Over the course of a decade, Friedman's team used Hubble to observe Cepheid variable stars in 18 galaxies, carefully calibrated against geometric distance measurements. In 2001, the Key Project published its final result, approximately 72 kilometers per second per megaparsec, with an uncertainty of about 10%. The answer landed almost exactly between Sandage and de Vaucouleurs. Neither camp had been entirely right. Neither had been entirely wrong. The war ended not with a victory, but with a compromise imposed by better data. That result held for years. It became the textbook value. 72, give or take. Close enough for most purposes. The age problem had been resolved decades earlier by the discovery that the expansion was accelerating, which changed the mathematical relationship between the Hubble constant and the age of the universe. Everything seemed settled. The number had been measured. The field could move on to other questions. Except that around the same time, Friedman's team was publishing its final key project results. A new generation of instruments was beginning to measure the universe from the other end, not by looking at nearby stars, but by looking at the oldest light in existence. And the number those instruments would eventually produce was not 72. The error came from the difficulty of measuring cosmic distances. Every estimate of the Hubble constant depends on knowing how far away things are. And measuring distance in the universe is one of the hardest problems in all of science. You cannot stretch a tape measure to another galaxy. You cannot bounce a radar signal off a star that is 50 million light-years away and wait for the echo. Instead, astronomers developed a chain of techniques, each one building on the last, reaching further and further into space with each step. That chain is called the cosmic distance ladder, and the accuracy of the Hubble constant depends entirely on how solid each rung of that ladder is. The first rung is geometry. Within our own galaxy, astronomers can measure the distance to nearby stars using parallax, the same principle that makes a nearby object appear to shift position when you close one eye and then the other. As Earth orbits the Sun, nearby stars appear to wobble slightly against the background of more distant ones. The amount of wobble tells you the distance. The European Space Agency's Gaia mission has measured parallax distances to over 1 billion stars with extraordinary precision. But parallax only works for stars close enough to show a detectable shift. Beyond a few thousand light-years, the wobble becomes too small to measure. That is where the second rung begins, Cepheid variable stars. These are a specific type of star that pulses in brightness in a regular cycle. They swell and shrink, brightening and dimming over periods that range from a few days to several weeks. The critical property of Cepheids, the reason they matter so much, is a relationship published in 1912 by Henrietta Swan Leavitt, a woman working at Harvard College Observatory at a time when female astronomers were not even permitted to operate the telescopes. Leavitt noticed that among Cepheids in the small Magellanic Cloud, a satellite galaxy of the Milky Way, the ones with longer pulsation periods were also brighter. The relationship was tight and predictable. If you know how long a Cepheid takes to complete one pulse, you know its true brightness. And if you know its true brightness and measure how bright it appears from Earth, you can calculate how far away it is. That is the power of Cepheids. They are cosmic yardsticks. You find one in a distant galaxy, time its pulse, and you have a distance. The third rung of the ladder reaches even further. Type Ia supernovae. These are thermonuclear explosions that occur in binary star systems. A white dwarf, the dense remnant of a dead star, accretes matter from a companion until it reaches a critical threshold, roughly 1.4 times the mass of the Sun, and detonates. The explosion is so violent it briefly outshines an entire galaxy. And because the trigger point is always roughly the same mass, the peak brightness of these explosions is approximately consistent. They are not perfect standard candles, but they can be standardized. Corrections for the shape and color of their light curves allow astronomers to calibrate their true luminosities. A type Ia supernova can be seen billions of light-years away, which means it can carry the distance measurement deep into the expansion of the universe. The chain works like this. Geometric parallax calibrates the distances to nearby Cepheids. Those Cepheids calibrate the distances to galaxies that also contain type Ia supernovae. And those supernovae then measure distances to galaxies so far away that the expansion of the universe dominates their motion. At the far end of the chain, you compare the distances to the velocities of recession and you calculate the Hubble constant. This is what the SH0ES team has been doing for nearly 20 years. Every step refined, every source of error hunted down and corrected. Dust that reddens starlight and makes distances look longer than they are accounted for. Metallicity differences in Cepheids across different galaxies corrected for. Calibration anchors cross-checked against independent geometric distances from Mars's, detached eclipsing binary stars in the Large Magellanic Cloud, and parallax measurements from Gaia. By the time the team published their landmark 2022 result, the measurement had been tested against every known systematic, more than 40 supernova-hosting galaxies. Over 1,000 individually resolved Cepheids, the answer held firm, approximately 73 kilometers per second per megaparsec. Precision better than 1.5%. That would have been a triumph, a clean resolution of a measurement that had been debated for nearly a century, except for one thing. The other method gave a different answer. The second way to determine the Hubble constant does not look at the nearby universe at all. It looks at the beginning. Approximately 380,000 years after the Big Bang, the universe cooled enough for hydrogen atoms to form for the first time. Before that moment, the cosmos was a blinding fog of charged particles. Photons could not travel in a straight line because they were constantly scattering off free electrons. When the atoms formed, the electrons were captured, the fog cleared, light was released in every direction. That light has been traveling through space ever since, stretching in wavelength as the universe expands, cooling from a white-hot glow to a faint whisper of microwave radiation. Today, it fills every cubic centimeter of space. It is the oldest light in the universe. Scientists call it the cosmic microwave background. In 2009, the European Space Agency launched the Planck satellite. Its mission was to map the cosmic microwave background with unprecedented precision. And it succeeded beyond expectations. Planck measured temperature fluctuations in this ancient light to an accuracy of millionths of a degree. Those tiny hot and cold spots are not noise. They are the frozen imprint of sound waves that rippled through the infant universe. Pressure waves in a plasma of matter and radiation, oscillating back and forth before the universe cooled and the waves froze in place. The size and spacing of those fluctuations encode an extraordinary amount of information. The total density of matter, the density of ordinary atoms, the density of dark matter, the geometry of space, the ratio of radiation to matter. Each parameter leaves a specific fingerprint in the pattern of hot and cold spots. By fitting a theoretical model to the observed pattern, scientists can extract these parameters with remarkable precision. The model they use is called lambda CDM. Lambda stands for the cosmological constant, Einstein's old mathematical term, now reinterpreted as dark energy. CDM stands for cold dark matter, the invisible substance that outweighs visible matter roughly 5-to-1 and provides the gravitational scaffolding on which galaxies form. Lambda CDM is the standard model of cosmology. It has been the reigning framework for over 2 decades. It successfully predicts the pattern of the cosmic microwave background, the distribution of galaxies on the largest scales, the abundances of light elements forged in the first minutes after the Big Bang, and the accelerating expansion discovered by Riess and his colleagues. When you feed Planck's data into lambda CDM and ask the model to predict the current expansion rate, the answer that comes back is approximately 67.4 kilometers per second per megaparsec, not 73, 67. And the uncertainty on that prediction is small, extremely small, less than 1%, which means the Planck value and the SH0 ES value do not overlap, not even at the edges of their error bars. They are separated by a gap of roughly 5 to 6 kilometers per second per megaparsec. That gap sounds small in ordinary terms. In cosmological terms, it is enormous, because both measurements claim to be precise to about 1%. A gap of 8% between two 1% measurements is not a gray area. It is a contradiction. Scientists have a way of quantifying how serious a disagreement like this is. They express it in units of sigma, a statistical measure of how many standard deviations separate two results. A 1 sigma difference is unremarkable. You expect that from normal measurement variation. A 2 sigma difference makes you look more carefully. A 3 sigma difference is considered strong evidence that something real is going on. A 5 sigma difference, in particle physics, is the threshold for claiming a discovery. It means the odds of the result being a statistical fluke are roughly 1 in 3.5 million. The Hubble tension, as of the most recent data, sits at approximately 5 sigma. 1 in 3.5 million odds that this is just noise. That is not a measurement error that will quietly go away with better instruments. That is a flashing signal that something fundamental is either wrong with one of the measurements or wrong with the model connecting them. For years, the most popular hope was that the problem lay with the measurements, specifically with the Cepheids. Looking at a Cepheid in a galaxy 100 million light-years away is not easy, even for the Hubble Space Telescope. In the densely packed inner regions of a distant galaxy, multiple stars can blur together in a single pixel. A Cepheid that appears as one bright dot might actually be a Cepheid sitting on top of several dimmer stars whose light blends in, making the Cepheid look brighter than it truly is. If it looks brighter, you calculate that it is closer. And if the distances to the host galaxies are systematically underestimated, the expansion rate you derive is systematically too high. This is the crowding hypothesis. And it was credible. Several prominent astronomers, including Wendy Friedman, the same scientist who led the original Hubble Key project in the 1990s, raised concerns about it publicly. Friedman argued that alternative distance indicators, ones less vulnerable to crowding, might give a lower expansion rate, closer to the Planck prediction. The debate was intense, data-driven, and legitimate. Both sides had strong arguments. Both sides had access to world-class data. But both sides also knew that there was one instrument that could settle the argument. One telescope with infrared eyes sharp enough to cut through dust, resolve individual stars in crowded fields, and see Cepheids more clearly than any instrument ever built. It had launched on Christmas Day, 2021, from a spaceport in French Guiana, aboard an Ariane 5 rocket. It had unfurled a sunshield the size of a tennis court, cooled its instruments to temperatures near absolute zero, and parked itself at a gravitational balance point roughly 1.5 million kilometers from Earth. It was the most expensive, most complex, most ambitious space observatory ever constructed. And one of the scientific justifications for building it was precisely this: to test whether the Hubble Space Telescope's measurements of the cosmic distance ladder were trustworthy, to either find the error that would dissolve the tension or confirm that no error existed. The James Webb Space Telescope turned its golden mirror toward the same galaxies, the same Cepheids, the same distance ladder that Riess had spent 2 decades refining. The data began coming in during 2023. The first results were published within months. And by late 2024, after the largest sample of Webb observations ever collected for this purpose had been analyzed, the answer was unambiguous. Webb saw the Cepheids more clearly than Hubble ever had. Its infrared vision sliced through dust that had complicated optical measurements. Its sharper resolution separated stars that had blurred together in Hubble's images. The crowding that critics had worried about was real in some cases, but it was not large enough to explain the tension, not even close. When every correction was applied and every cross-check completed, Webb's Cepheid-based expansion rate landed at approximately 72.6 kilometers per second per megaparsec. Hubble's value for the exact same galaxies was 72.8. The two telescopes agreed to within a fraction of a percent. Riess put it plainly, "We have now spanned the whole range of what Hubble observed, and we can rule out a measurement error as the cause of the Hubble tension with very high confidence." And then he said the sentence that changed the tone of the entire field. With measurement errors negated, what remains is the real and exciting possibility that we have misunderstood the universe. Exciting. He used the word exciting. But listen to what that sentence actually says. The most precise local measurement of cosmic expansion has been confirmed by the most powerful telescope ever built. The most precise early universe prediction of cosmic expansion has been confirmed by the most detailed map of the cosmic microwave background ever made. Both are right, and they do not agree. The instruments are working. The stars are not lying. The model that connects the infant universe to the present universe is producing a prediction that does not match what the present universe actually shows. That is not a technical glitch. That is a crack in the foundation. And everything that follows in this story is about how deep that crack runs and what might be hiding underneath it. Because what happened next was not a single dramatic revelation. It was something quieter and in many ways more unnerving. One by one, other teams using completely different methods began reporting their own expansion rate measurements. And one by one, they kept landing on the same side of the divide. The late universe kept saying 70-ish, the early universe kept saying 67, and the gap refused to close. The world's most powerful space telescope had been handed the simplest possible assignment. Look at the stars, check the distances, tell us who is right. Instead, it confirmed that both sides are right. And that is the problem. Because in a universe governed by one consistent set of physical laws, two correct answers that contradict each other is not supposed to happen. Something beyond our current understanding is shaping the way this universe expands. And finding out what that something is has become the most urgent, open question in modern cosmology. The Cepheids were clean. The ladder was solid, the tension was real, and the race to explain it was about to expose cracks that ran far deeper than anyone had expected. We have just established the core contradiction. Two measurements, both precise, both confident, both pointing to different numbers. But to truly feel why this contradiction is so dangerous for modern cosmology, you need to understand something deeper. These are not two random techniques that happen to disagree. They are two ends of a single logical chain. The early universe measurement and the late universe measurement are connected by a model. That model is the entire framework through which we interpret the cosmos. And what the Hubble tension is really testing is not whether our telescopes work, it is whether our framework does. Think of it this way. Imagine you photograph a child on the day they are born. You record their weight, their length, the circumference of their head, every detail you can capture. Then you feed all of that information into the most accurate growth model ever built. a model that accounts for genetics, nutrition, environment, everything we know about how human bodies develop. The model predicts that by age 30, this child should be 5 feet 9 inches tall. You wait 30 years, you measure the adult, they are 6 feet 2. The model was not built carelessly. The birth measurements were not wrong, but the prediction and the reality do not match. Something happened between birth and adulthood that the model did not account for. Something about the way this person grew is different from what the model expected. That is the Hubble tension. The cosmic microwave background is the birth photograph. Planck's data captured every detail of the infant universe with extraordinary precision. Lambda CDM is the growth model. It takes those infant measurements and evolves them forward through 13.8 billion years of cosmic history, predicting what the universe should look like today. And one of its key predictions is the current expansion rate, 67.4. The local measurements, the distance ladder, the supernovae, the Cepheids, all of that is the tape measure held up to the adult universe right now. And the adult does not match the prediction. Not by a little, by enough to be statistically impossible to ignore. This is what makes the Hubble tension different from an ordinary scientific disagreement. It is not two groups of scientists arguing over whose instrument is better calibrated. It is the entire growth model of the cosmos producing a prediction that reality contradicts. If both measurements are correct, the model is wrong. And the model is everything. Lambda CDM has been the governing framework of cosmology for over 2 decades. It is not a speculative theory. It is a quantitative, predictive, battle-tested mathematical structure. It tells you the age of the universe. It tells you how much matter there is, how much dark energy, how much radiation. It predicts the pattern of temperature fluctuations in the cosmic microwave background to exquisite accuracy. It predicts how galaxies cluster together on scales of hundreds of millions of light-years. It predicts the relative abundances of hydrogen, helium, and lithium forged in the first few minutes after the Big Bang. Every time a new dataset has come in over the past 20 years, Lambda CDM has passed the test, not vaguely, precisely, decimal point by decimal point. This is the model that says the expansion rate should be 67. To understand why that prediction is so robust, you need to understand what happens inside the mathematics when Planck's data enters the model. The cosmic microwave background carries an imprint called the sound horizon. Before the universe cooled enough for atoms to form, matter and radiation were locked together in a hot plasma. Pressure waves, essentially sound waves, rippled through this plasma at a speed determined by the ratio of radiation to matter. Those waves traveled for roughly 380,000 years, from the moment the universe began until the moment the plasma cooled and the waves froze. The distance each wave had crossed by the time it froze is the sound horizon. It is a fixed physical length baked into the structure of the early universe. That length shows up in the cosmic microwave background as a characteristic angular size of the hot and cold spots. It also shows up in the distribution of galaxies today as a preferred separation distance called the baryon acoustic oscillation scale. In both cases, you are seeing the same ruler. The sound horizon measured at the beginning of time, stretched by the subsequent expansion of space to the size it appears today. If you know the physical length of the ruler and you know the angular size it appears on the sky, you know the distance to the surface where the microwave background was emitted. And from that distance, combined with the time that has elapsed, you can work backward to calculate the expansion rate. The precision of this calculation is breathtaking. Planck measured the angular size of the sound horizon to better than 0.1%. The physics of the pre-recombination plasma is well understood. The model has only 6 free parameters, and each one is constrained tightly by the data. There is very little wiggle room. When you turn the crank on lambda CDM with Planck's inputs, 67.4 is not a rough estimate. It is the answer the model gives with deep confidence, and that is the problem. Because the model's confidence makes the disagreement harder to dismiss. If the prediction were loosely constrained, if the error bars were wide, you could wave the tension away as statistical noise. You cannot do that when both sides claim 1% precision and the gap between them is 8%. Something is off. Either the early universe data is subtly contaminated, or the late universe data is subtly contaminated, or the model that bridges them is missing a piece. For over a decade, the scientific community pursued the first two explanations with enormous effort before even seriously entertaining the third. The story of that pursuit is the story of the Hubble tension growing from a curiosity into a crisis. And it is worth telling in some detail because it reveals how science actually works when something fundamental might be wrong. The tension was not born all at once. It grew. In the early 2000s, estimates of the Hubble constant from the distance ladder were scattered. Different groups got values ranging from the low 60s to the mid-70s, depending on which Cepheids they used, which calibrations they trusted, which corrections they applied. The error bars were wide enough that most of these results overlapped. Nobody was alarmed. Then, the Hubble Space Telescope observations improved. The SH0ES team refined their techniques year by year. Their value crept upward and stabilized around 73. Their error bars shrank. Simultaneously, the WMAP satellite and then Planck delivered increasingly precise maps of the cosmic microwave background. The early universe prediction stabilized around 67. Its error bars shrank too. By roughly 2016, the two values were clearly separated. But many scientists expected the problem to resolve itself. Measurement errors are common in astronomy. Complex calibrations can hide subtle biases. The assumption was that someone, somewhere, was making a mistake, and sooner or later the mistake would be found. It was not found. Every year, new data came in. Every year, the gap held. In 2018, Riess's team published a comprehensive measurement with precision below 2%. Planck published its final data release the same year, with a value of 67.4 and an uncertainty of less than 1%. The tension was above 4 sigma. Papers began appearing in the literature with titles that used words like crisis and discordance and new physics. The community was beginning to take the problem seriously. But a significant faction still held that the answer lay in systematic errors, specifically in the Cepheid measurements. Wendy Friedman was the most prominent voice in this camp, and her credibility was enormous. In the 1990s, she had led the Hubble Space Telescope Key project, the definitive effort of its era to measure the Hubble constant. Her team's result at the time, approximately 72, established the benchmark that the field used for years. She knew the distance ladder better than almost anyone alive. And she had concerns. Her primary worry was Cepheids, not their physics, which is well understood, but their observational complications. Cepheids tend to live in the crowded, dusty disk regions of galaxies. When you observe them with the Hubble Space Telescope, particularly in galaxies beyond about 30 million light-years, you are looking at a region where hundreds or thousands of stars can occupy a single resolution element. The light of faint background stars blends with the light of the Cepheid. You cannot separate them optically. This means the Cepheid appears brighter than it truly is, and if it appears brighter, you calculate that it is closer. Systematic overestimation of brightness leads to systematic underestimation of distance, which inflates the Hubble constant. The SH0ES team was well aware of this concern. They had developed detailed statistical methods to account for crowding effects, estimating the average contamination from unresolved stars and correcting for it. Their corrections had been tested and cross-validated internally. They argued that crowding could not explain the full gap. Friedman was not convinced. She advocated for alternative distance indicators that are less susceptible to crowding, two in particular. The tip of the red giant branch, which measures the brightest red giant stars in the halos of galaxies, where stellar densities are low and crowding is minimal. And the J-region asymptotic giant branch method, which uses carbon-rich giant stars that have remarkably uniform infrared luminosities, making them natural standard candles. In 2020, Friedman published a measurement using the tip of the red giant branch method that yielded a Hubble constant of approximately 69.8. This sat squarely between the Planck value and the SH0 value. She argued that this intermediate result was consistent with the standard model and suggested the tension might dissolve once Cepheid-based measurements were replaced with cleaner alternatives. But the result was contested. Other groups analyzing the same red giant data with different calibrations obtained higher values, closer to 72 or 73. The disagreement hinged on technical choices about how to set the zero-point brightness of the red giant branch, which depends on accurate distance measurements to calibrating galaxies. The debate became intense and, at times, personal. Both camps published detailed rebuttals of each other's analyses. For several years, the field was gridlocked. This is the context in which James Webb entered the picture. Not as a neutral observer, but as an arbiter. The telescope's infrared instruments offered a resolution to the specific technical disagreement at the heart of the standoff. Webb's mirror is 6.5 meters across, compared to Hubble's 2.4. Its infrared detectors operate at wavelengths where dust is nearly transparent and where the contrast between a Cepheid and its fainter neighbors is sharper. If crowding was secretly inflating the Cepheid distances, Webb would see it. Stars that blurred together in Hubble's images would separate cleanly in Webb's. Both teams were awarded observing time. Riess's SH0 team and Friedman's Chicago Carnegie Hubble program each received allocations in Webb's first and second cycles. They observed overlapping sets of galaxies, using the same telescope but applying their own methods and calibrations. The results were published in 2024, and they did not tell a simple story. The SH0 team's results were unambiguous. They examined Cepheids across the full range of galaxies previously studied by Hubble out to the most distant hosts at roughly 130 million light-years. Webb's images confirmed what Riess had argued for years. The Cepheids were real. They were not artifacts of blending. Their brightness measurements from Webb agreed with those from Hubble to a degree that left no room for crowding to explain the tension. The team also cross-checked their Cepheid distances against tip of the red giant branch and carbon star measurements in the same galaxies. Everything converged. Their combined Webb-based Hubble constant came in at 72.6. Friedman's results were more nuanced. Her team observed 10 galaxies using all three methods: Cepheids, tip of the red giant branch, and J-region asymptotic giant branch stars. For the TRGB and JGB methods, her values came in lower, around 68 to 70, suggesting alignment with the standard model. Her Cepheid value from Webb was higher, around 72, but with larger uncertainties due to the smaller sample. When she combined all three methods, her headline number was approximately 70, and she stated publicly that based on her new data, she did not find strong evidence for a Hubble tension. This sounds like it should have diffused the crisis. It did not. And the reasons why illuminate just how deep the problem runs. First, Friedman's own numbers tell a more complicated story than her summary suggests. Her TRGB and JAGB values, while lower than SH0 still sit above the Planck prediction of 67. Her best overall TRGB estimate, combining Hubble and Webb data, was approximately 70.4. That is lower than 73, yes. But it is still higher than 67 by a margin that is not trivially explained. Even by Friedman's own measurements, the early universe prediction is not comfortably reached. Second, the discrepancy between Friedman's TRGB and JEG-B distances and the SH0ES Cepheid distances for the same galaxies created a new puzzle. The methods agree at the 1 to 2% level in terms of raw distances, which is impressive. But a persistent offset of 2.5 to 4% between Cepheid distances and the other two methods suggests either an unresolved calibration difference or a genuine physical effect that the field does not yet understand. That offset matters because it is large enough to shift the Hubble constant by the amount needed to close or open the tension. Third, and perhaps most importantly, while Riess and Friedman debated the fine details of the distance ladder, other teams using completely independent methods were quietly publishing their own results. And those results did not support the idea that the tension was an artifact of Cepheid measurements. In December 2025, the TD-Cosmo collaboration published a landmark result. This team measures the Hubble constant using an entirely different physical phenomenon, gravitational lensing. When a massive galaxy sits between us and a more distant bright object like a quasar, the galaxy's gravity bends the light, creating multiple images of the background quasar. These images flicker as the quasar varies in brightness, but the flickers arrive at slightly different times because the light has traveled along paths of different lengths. By measuring the time delay between the images and modeling the mass distribution of the lensing galaxy, you can calculate the distances involved, and from those distances you can derive the Hubble constant. No Cepheids, no supernovae, no cosmic microwave background, no distance ladder at all, a completely independent path to the same number. That contradiction was not a minor footnote. It was a full-blown embarrassment for the young science of cosmology. Geologists had radioactive dating. They could measure the age of rocks with confidence. And the rocks said Earth was at least 3 billion years old, probably closer to 4.5. If Hubble's expansion rate was right, the universe had to be younger than the planet sitting inside it. The mathematics did not allow both to be true. For decades, the problem festered. Different astronomers using different techniques arrived at wildly different values for the Hubble constant. By the 1970s, the field had split into two hostile camps. On one side was Alan Sandage, Hubble's intellectual successor at the Mount Wilson and Palomar observatories, who favored a value around 50. On the other was Gérard de Vaucouleurs, a French-born astronomer working in Texas, who argued for a value near 100. The difference was not a minor academic quibble. A Hubble constant of 50 implied a universe roughly 20 billion years old. A value of 100 implied a universe of roughly 10 billion years, uncomfortably close to the ages of the oldest known stars. The two camps published competing results for years, each questioning the other's calibrations, dust corrections, and choice of distance indicators. Conferences became battlegrounds. Careers were defined by which side you took. The Hubble constant wars, as they came to be called, were among the most bitter scientific disputes of the 20th century. The war was not resolved by argument. It was resolved by a telescope. In 1990, NASA launched the Hubble Space Telescope into orbit above the blurring effects of Earth's atmosphere. One of its primary scientific missions, designated the Key Project, was to measure the Hubble constant with enough precision to end the debate. The project was led by Wendy Friedman, a young astronomer who would go on to become one of the most influential figures in the field. Over the course of a decade, Friedman's team used Hubble to observe Cepheid variable stars in 18 galaxies, carefully calibrated against geometric distance measurements. In 2001, The Key project published its final result, approximately 72 kilometers per second per megaparsec, with an uncertainty of about 10%. The answer landed almost exactly between Sandage and de Vaucouleurs. Neither camp had been entirely right. Neither had been entirely wrong. The war ended not with a victory, but with a compromise imposed by better data. That result held for years. It became the textbook value, 72, give or take, close enough for most purposes. The age problem had been resolved decades earlier by the discovery that the expansion was accelerating, which changed the mathematical relationship between the Hubble constant and the age of the universe. Everything seemed settled. The number had been measured. The field could move on to other questions. Except that around the same time, Friedman's team was publishing its final Key project results. A new generation of instruments was beginning to measure the universe from the other end, not by looking at nearby stars, but by looking at the oldest light in existence. And the number those instruments would eventually produce was not 72. The physics behind gravitational lensing cosmography is worth pausing on, because its independence from every other method is what makes it so powerful. When a massive galaxy sits almost directly between us and a distant quasar, the galaxy's gravitational field warps the fabric of space-time around it. Light from the quasar does not travel in a single straight line to Earth. It follows multiple curved paths around the lensing galaxy, like water flowing around a rock in a stream. From our perspective, we see not one image of the quasar, but several, typically 2 or 4, arranged in an arc or a cross pattern around the central galaxy. Each image is a copy of the same quasar, but each copy's light has traveled a different route through curved spacetime. Quasars are not static objects, they flicker. Their brightness varies irregularly as matter spirals into the supermassive black hole at their center. When a quasar brightens or dims, we see that change appear in each of the lensed images, but not simultaneously. Because each path has a different length and passes through a different amount of curved spacetime, the flickers arrive at slightly different times. One image might show a brightness spike on a Monday, another shows the same spike on a Thursday. The delay between them can be days, weeks, or even months, depending on the geometry. That time delay is a direct measurement of the difference in path length between the two images. And the path length depends on the distances involved, the distance from us to the lensing galaxy, the distance from us to the quasar, and the distance from the lensing galaxy to the quasar. All of these distances depend on how the universe has expanded between those objects and us. By measuring the time delay and modeling the mass distribution of the lensing galaxy, you can extract the Hubble constant. The beauty of this method is that it depends on completely different physics from anything in the distance ladder. There are no pulsating stars to calibrate. There are no supernova explosions to standardize. There is no chain of measurements where one rung depends on the last. It is a single-step measurement that goes directly from an observable quantity, the time delay, to a cosmological parameter, the expansion rate. If there are hidden systematic errors in the Cepheid measurements, the lensing method does not inherit them. If there are problems with how type Ia supernovae are calibrated, the lensing method is unaffected. The two approaches share no common failure modes. The TD Cosmo 2025 analysis used 8 gravitationally lensed quasar systems, incorporating new kinematic data from Webb's own NIRSpec instrument for 6 of those systems, along with observations from the Very Large Telescope and the Keck Observatory. Their result was approximately 71.6 kilometers per second per megaparsec, firmly on the late universe side. Kenneth Wong, one of the team's lead researchers at the University of Tokyo, put it directly. Their measurement is more consistent with other late universe observations and less consistent with early universe measurements. He called it evidence that the Hubble tension may arise from real physics and not from unknown sources of error. The significance of this result is hard to overstate. The entire critique of the distance ladder rested on the idea that some subtle, systematic, crowding, dust, calibration might be inflating the local expansion rate. Gravitational lensing sidesteps all of those concerns. It uses different physics, different objects, different data, different telescopes, and it gets the same answer. 70-ish, not 67. Another independent team reached a similar conclusion using yet another method. Joseph Jensen and colleagues used surface brightness fluctuations, a technique that measures the graininess of the light from elliptical galaxies to determine their distances. The physics is elegant. Closer galaxies look grainier because you can partially resolve individual stars. More distant galaxies look smoother. By quantifying this smoothness and calibrating it against known distances, you can build a distance ladder that bypasses Cepheids entirely and does not rely on type Ia supernovae for the final step. Jensen's team, using Webb data to calibrate their measurements, arrived at a Hubble constant of approximately 73.8, again squarely on the late universe side. At the January 2025 meeting of the American Astronomical Society, Duke University astrophysicist Dan Skolnick stood before his colleagues and declared that the Hubble tension was now a crisis. His language was not casual. In the restrained world of academic cosmology, calling something a crisis is a strong statement. It means the evidence has passed the threshold where the field can no longer treat this as a problem that might go away with better data. The data kept getting better. The problem kept not going away. To appreciate the weight of that word, crisis, you need to understand how conservative the culture of cosmology normally is. Astronomers do not use dramatic language lightly. Papers are written in the passive voice. Conclusions are hedged with caveats. Phrases like, "our results are consistent with," and "further observations are needed," fill the literature. When a respected researcher at a major professional meeting stands up and uses the word crisis without qualification, it signals something specific. It means the accumulated evidence has reached a point where the normal mechanisms of scientific caution are no longer adequate to describe the situation. The professional norms that usually dampen strong claims have been overridden by the data itself. Skolnick's declaration did not come in isolation. Over 500 researchers from institutions across Europe and beyond had recently formed the Cosmoverse Consortium specifically to address the growing landscape of tensions between cosmological theory and observation. Their white paper, published in 2025, laid out the full scope of the problem. The Hubble tension was the centerpiece, but it sat alongside the Cepheid tension in matter clustering, hints of evolving dark energy from DESI, anomalies in the cosmic microwave background at small angular scales from the Atacama Cosmology Telescope, and the unexpectedly massive galaxies Webb had discovered in the early universe. The consortium did not claim that any single anomaly was fatal to the standard model. What they argued was that the pattern of anomalies, taken together, created a level of pressure on lambda CDM that the field had never previously faced. By this point, the landscape looked like this. The SH0ES Cepheid distance ladder, confirmed by Webb, gives approximately 73. Friedman's TRGB method gives approximately 70, depending on the calibration. Jensen's surface brightness fluctuation method gives approximately 74. The TD Cosmo gravitational lensing method gives approximately 72. Every late universe method, regardless of the objects used, the telescopes employed, or the physics invoked, lands somewhere between 69 and 74. The early universe prediction based on Planck and lambda CDM insists on 67. Even in the most generous reading, where you take Friedmann's lowest values and argue that the tension is reduced to 2 or 3 sigma, the Planck prediction is not reached. And, in the reading supported by the broadest convergence of independent methods, the tension remains above 4 sigma, with multiple lines of evidence pointing toward the same conclusion. The late universe is expanding faster than the early universe says it should be. This is the moment where the conversation has to shift. For a decade, the debate was about instruments and calibrations and systematic errors. Was Hubble seeing the Cepheids clearly enough? Were the dust corrections right? Was the tip of the red giant branch properly calibrated? Those were legitimate questions, and Webb answered them. The instruments are fine. The calibrations hold up. The methods agree with each other. The problem is not observational, which means the problem is theoretical, and that realization changes the stakes entirely. Because if the standard model of cosmology is the source of the discrepancy, then the implications reach far beyond one number. Lambda CDM does not just predict the expansion rate, it predicts the age of the universe, the amount of dark matter, the behavior of dark energy, the growth of cosmic structure, the geometry of space. If the model is wrong about the expansion rate, it may be wrong about other things too. And there are signs emerging from independent lines of evidence that it might be. The European Research Council recognized the severity of the situation. In 2025, it awarded a €12 million synergy grant to a project called REDH0T, short for Red Teaming the H0 Tension. The project, co-led by cosmologists Licia Verde and Frédéric Courbin, employs a deliberate adversarial approach. Red teaming means actively trying to break a system, probing it for weaknesses, challenging every assumption, testing every method for hidden flaws. The fact that a major research council funded a project whose entire purpose is to stress test the foundations of modern cosmology tells you something about how seriously the field is now taking the problem. What makes all of this so disquieting is not that the answer is wrong. It is that we do not yet know what the right answer looks like. The model that has worked for 20 years may need to be modified. The question is how. And every proposed modification carries consequences that ripple through the entire structure of cosmology. The simplest hope was always that better data would make the problem disappear. James Webb was that better data. It arrived, it observed, and instead of resolving the tension, it eliminated the most appealing escape route. The expansion rate measured from the nearby universe is what it is. The prediction from the early universe is what it is. And the space between those two numbers is where modern cosmology now lives. Suspended between a model that has worked beautifully for decades and a set of measurements that say the model is not the whole story. Something is woven into the fabric of the cosmos that we do not yet understand. That phrase, from the European Space Agency's own summary of Webb's Hubble tension results, is as close to a public admission of bewilderment as a major scientific institution typically allows itself. The fabric of the cosmos, woven into it, not tacked onto the edges, not hiding in the error bars. Built into the structure of reality in a way that 20 years of precision cosmology failed to detect. Whatever the answer turns out to be, it will not be small. You do not get a 5 sigma tension between the most precise measurements in the history of cosmology and fix it with a minor adjustment. Something about the way the universe expanded between its infancy and today is different from what our best model predicts. That difference has now been confirmed by multiple teams, multiple methods, and the most powerful space telescope ever built. The instrument spoke, the universe answered. And the answer was not what anyone expected. Now the question becomes what is missing from the model? What ingredient, what force, what behavior have we overlooked? The candidates range from subtle revisions to radical departures. None of them are proven. Several of them are fascinating. And all of them carry the implication that our picture of the universe, the picture that has served as the foundation of cosmology for a generation, is incomplete in ways we are only beginning to map. The moment the measurements were confirmed, the question changed. For over a decade, the Hubble tension had lived in a space where reasonable scientists could disagree about whether the problem was real. Maybe the Cepheids were contaminated. Maybe the dust corrections were slightly off. Maybe the tip of the red giant branch calibration needed adjustment. There were enough technical loose threads that a careful skeptic could look at the gap between 67 and 73 and say, this might still be a measurement problem. We just need better data. Webb delivered the better data, and the gap did not close. That single fact altered the scientific landscape in a way that no amount of theoretical speculation had managed to do. The conversation in cosmology shifted, not overnight, not with a dramatic announcement or a front-page revelation, but steadily, paper by paper, conference by conference, the center of gravity moved from, are the measurements right, to what is wrong with the model. And the answers that began emerging were more uncomfortable than the question. When physicists say the standard model of cosmology might be incomplete, they are not suggesting that everything we know is wrong. Lambda CDM has survived 2 decades of increasingly precise observations without a single confirmed failure. Every major cosmological dataset collected since the turn of the millennium has landed within its predictions. No competing framework comes close to matching its track record. That is what makes the Hubble tension so difficult to process. The model being challenged is not a rough sketch or a first draft. It is the most thoroughly validated quantitative framework in the history of cosmology, a structure built on general relativity, nuclear physics, thermodynamics, and fluid dynamics, held together by only 6 free parameters and confirmed across observations spanning billions of light-years and billions of years. A persistent 8% disagreement in one of its most fundamental predictions is not something this model is supposed to produce. If the framework were loosely constrained, the tension would not matter. Because the framework is precise, the tension matters enormously. The first serious theoretical attempt to resolve the Hubble tension without abandoning lambda CDM entirely goes by the name early dark energy. The idea was developed in its modern form primarily by Vivian Pouline and collaborators, building on earlier work by Tanvi Karwal and Mark Kamionkowski. The concept is elegant in its simplicity. What if there was a brief burst of extra energy in the universe just before recombination, the moment when the cosmic microwave background was released? To understand why this would help, you need to go back to the sound horizon. The sound horizon is the distance that pressure waves traveled through the early plasma before recombination froze them in place. That distance depends on 2 things: the speed at which the waves moved, which is determined by the composition of the plasma, and the amount of time the waves had to travel, which is determined by when recombination happened. Lambda CDM fixes both of these with high precision based on Planck's data. The result is a specific sound horizon length, and from that length flows the prediction of 67 for the Hubble constant. Now, imagine adding a new ingredient: a brief pulse of energy that appears just before recombination and then vanishes rapidly afterward. This extra energy would increase the overall expansion rate of the universe during that narrow window of time. A faster expansion rate means the universe was evolving more quickly, which means recombination happened slightly earlier. If recombination happened earlier, the sound waves had less time to travel. A shorter travel time means a smaller sound horizon, and here is the crucial link. If the sound horizon is smaller than lambda CDM predicts, then the angular size of the fluctuations in the cosmic microwave background corresponds to a shorter physical distance. To make that shorter distance consistent with the angular pattern Planck actually observed, you need the universe to have been expanding faster. The predicted Hubble constant goes up, closer to 73. Tension reduced. On paper, it works. In practice, it runs into walls. The first wall is the cosmic microwave background itself. Planck's data is not just a picture of spots on the sky. It is a power spectrum, a detailed measurement of how much fluctuation exists at every angular scale. Adding early dark energy changes the sound horizon, but it also changes other features of the power spectrum. It shifts the relative heights of the peaks. It alters the damping tail at small angular scales. It affects the way gravitational lensing, by intervening matter, smears the background pattern. When you fit an early dark energy model to the full Planck dataset, the improvement in the Hubble constant comes at the cost of a worse fit to other parts of the data. The model trades one tension for several smaller ones. The second wall is even more troublesome. It involves a separate cosmological measurement called Cepheid. This parameter describes how clumpy matter is in the present-day universe on scales of roughly 8 megaparsecs. Weak gravitational lensing surveys, which measure how the shapes of distant galaxies are subtly distorted by the gravity of matter between them and us, provide a direct measurement of this clumpiness. The value they find is consistently lower than what lambda CDM predicts based on Planck. This disagreement is called the Cepheid tension. It is smaller than the Hubble tension, typically around 2 to 3 sigma, but it has been persistent across multiple independent surveys. Early dark energy makes the Cepheid tension worse. Here is why. To compensate for its effects on the cosmic microwave background, the early dark energy model requires a higher density of cold dark matter. More dark matter means more gravitational clumping. More clumping means a higher Cepheid. But observations say Cepheid is already too high in the standard model. Pushing it further in the wrong direction does not solve the problem. It compounds it. This is the cruel mathematics of precision cosmology. The parameters are not independent. They are coupled to each other through the physics of the model. Pulling one lever to fix one tension inevitably moves another lever in a direction you did not want. The system resists isolated repairs. Researchers have not given up on early dark energy. Modified versions of the idea continue to be explored. Models where the scalar field driving the early dark energy decays in different ways. Models that combine early dark energy with other modifications. Models that adjust the equation of state of the dark energy component to minimize the collateral damage. Some of these show promise. None of them have achieved what the field would consider a clean solution, one that resolves the Hubble tension without worsening any other observable. While theorists wrestled with early dark energy, observational cosmology delivered another complication from an unexpected direction. In 2024, the Dark Energy Spectroscopic Instrument, known as DESI, published its first-year results from a survey of baryon acoustic oscillations. DESI maps the three-dimensional distribution of galaxies across cosmic time, measuring the imprint of the sound horizon at different epochs. This allows it to trace how the expansion rate of the universe has changed over the past 11 billion years. Lambda CDM makes a specific prediction about this history. Dark energy, modeled as a cosmological constant, has a fixed energy density that does not change as the universe expands. The cosmological constant is constant. That word is not decorative. It is the core assumption. The expansion history that follows from a constant dark energy is a smooth, predictable curve. DESI's data hinted that the curve might not be smooth. When the team fitted models that allowed dark energy to evolve over time, to change its strength as the universe aged, they found a mild preference for evolution over constancy. Specifically, the data favored a scenario where dark energy was stronger in the past and has weakened over time. The statistical significance was modest, around 2 to 3 sigma in the initial analysis, not enough to overturn the cosmological constant by itself, but the hint was tantalizing. And it pointed in a direction that connects directly to the Hubble tension. If dark energy is not a constant, then the expansion history of the universe is different from what lambda CDM assumes. A different expansion history means the sound horizon might be a different length. It means the distances inferred from baryon acoustic oscillations shift. It means the relationship between the early universe measurements and the late universe measurements passes through a different physical path. In principle, evolving dark energy could help reconcile the two values of the Hubble constant. In principle. In practice, the situation is more complex. A 2025 analysis by Zhang, Chen, and colleagues, using DESI's second data release combined with Planck and supernova data, tested 5 different dark energy models against the observations. Their findings were sobering. Across all 5 models, the Hubble tension persisted. No alternative dark energy framework achieved a statistically significant advantage over lambda CDM in resolving the discrepancy. The authors found compelling evidence that dark energy evolves with cosmic time, which itself is a major claim. But that evolution alone does not close the gap between 67 and 73. The reason is structural. The Hubble tension is fundamentally a disagreement between early universe physics and late universe physics. Modifying dark energy changes the late universe expansion history, but the Planck prediction of the Hubble constant is anchored in early universe physics. The sound horizon is set before dark energy becomes significant. To change the prediction, you either need to modify what happened before recombination, which is the early dark energy approach, or you need to modify the model in a way that simultaneously affects both regimes. No single ingredient modification has managed this cleanly. Meanwhile, Webb itself was delivering a parallel line of evidence that added further pressure to the standard model. In its first 2 years of deep field observations, the telescope discovered galaxies in the early universe that were far more massive and far more mature than lambda CDM predicted they should be. Some of these systems, observed when the universe was less than 500 million years old, contained stellar populations equivalent to billions of suns. Standard models of galaxy formation, which are built on top of lambda CDM's predictions for how dark matter clumps together over time, could not easily produce galaxies that large that early. This is a separate problem from the Hubble tension, but it is not unrelated. The rate at which structure forms in the universe depends on the same parameters that determine the expansion rate. The density of dark matter, the behavior of dark energy, the initial conditions encoded in the cosmic microwave background, all of these feed into both the Hubble constant prediction and the galaxy formation timeline. If the model is getting the expansion rate wrong, it may also be getting the structure formation rate wrong. The unexpectedly massive early galaxies are not proof of this connection, but they are consistent with it. They are another data point, suggesting that lambda CDM's description of the first billion years of cosmic history may be missing something. Intriguingly, some researchers have explored whether early dark energy might simultaneously address both problems. A 2024 study by Xuejian Shen and colleagues showed that the same early dark energy model that raises the predicted Hubble constant also changes the cosmological parameters in a way that enhances the abundance of dark matter halos at high redshift. More halos means more sites for galaxies to form. More formation sites means more massive galaxies appearing earlier. The early dark energy model, as a byproduct of solving the Hubble tension, naturally produces a universe with more early structure. Whether this fully accounts for Webb's observations remains an open question, but the overlap is striking. A single modification to the model, motivated entirely by the expansion rate disagreement, turns out to address a completely separate anomaly. That kind of convergence is what physicists look for when they suspect they are on the right track. When a proposed fix for one problem accidentally improves a different problem, it suggests the fix is touching something real. It does not prove it, but it raises the stakes. Early dark energy is not merely a mathematical patch for one number. It may be pointing toward a genuine feature of the early universe that lambda CDM has been missing. But the community remains divided. At the January 2025 meeting of the American Astronomical Society, the same meeting where Skolnick declared the Hubble tension a crisis, the debate between the SH0ES and Chicago Carnegie camps played out in real time. Friedman presented her latest JWST results and maintained her position that the tension could be significantly reduced, perhaps eliminated, if the field moved beyond Cepheids to the tip of the red giant branch and carbon star methods. Riess presented his team's comprehensive analysis and argued that the convergence of multiple independent methods on the high side made it increasingly unlikely that the tension was an artifact of any single distance indicator. The exchange was collegial, but pointed. What struck many observers was not the disagreement itself, but the fact that even Friedman's most optimistic numbers did not reach Planck's prediction. Her combined JWST-based value of approximately 70 sat closer to the SH0ES result than to the Planck result. The floor she was offering was still above the ceiling the standard model allowed. And multiple independent methods that bypass Cepheids entirely, the TD Cosmo lensing result at 71.6, the Jensen surface brightness fluctuation result at 73.8, kept piling onto the late universe side. This pattern reveals something important about where the scientific consensus actually stands. The debate within the late universe community is not about whether the expansion rate is higher than Planck predicts. Nearly everyone measuring the nearby universe gets a number above 68. The debate is about how much higher, whether it is 70 or 73 or somewhere in between. That is a meaningful difference for some theoretical models, but it is a difference within a range that uniformly excludes the Planck value. The gap between the late universe and the early universe has been narrowed by some analyses, but closed by none. Other proposed solutions populate the theoretical literature in growing numbers. Some involve modifying gravity itself. In general relativity, the relationship between matter, energy, and the geometry of space is fixed by Einstein's field equations. But general relativity has never been tested with the same precision in cosmological contexts that it has been tested in, say, the solar system. It is conceivable that gravity behaves slightly differently on the largest scales or at the earliest times. Modified gravity theories, including scalar tensor theories and certain versions of massive gravity, can in principle alter the expansion rate prediction. But like early dark energy, they tend to improve one fit while degrading another. Some proposals invoke new particles. Additional species of neutrinos or other light relics from the early universe would increase the radiation density before recombination, speeding up the expansion and shrinking the sound horizon. This is conceptually similar to early dark energy, but achieved through a different mechanism. The constraint on this idea is tight. The number of effective neutrino species is well measured by both the cosmic microwave background and by Big Bang nucleosynthesis, the process that produced the lightest elements in the first few minutes. There is only a small window of room for additional species, and it is not clear whether that window is large enough to resolve the tension. To grasp why the sound horizon is so central to every proposed solution, picture it this way. Imagine you are standing in a stadium after a concert has ended. The musicians played one final sustained note before the sound system was switched off. That note was a pressure wave in air, and it traveled outward from the speakers at the speed of sound. By the time the system cut out, the wave had crossed a specific distance determined by how fast sound travels in air and how long the note was sustained. That distance is frozen. It does not change afterward. You could measure it by finding the outer edge of where the sound reached. The sound horizon in the early universe works on the same principle, except the medium is not air. It is a plasma of protons, electrons, and photons, and the pressure waves moved at roughly half the speed of light. The note was sustained for approximately 380,000 years from the beginning of the universe until atoms formed and the plasma cooled. By the time the music stopped, the waves had crossed a distance of roughly 150 megaparsecs in today's stretched-out units. That distance is baked into the structure of the universe. It shows up in the cosmic microwave background as the characteristic spacing of the hot and cold spots. It shows up in the distribution of galaxies as a preferred clustering scale called the baryon acoustic oscillation peak. Every proposed resolution to the Hubble tension ultimately comes down to the sound horizon. If you believe the sound horizon is smaller than lambda CDM calculates, the predicted Hubble constant rises toward 73. Early dark energy achieves this by speeding up the expansion before recombination, so the waves had less time to travel. Extra neutrino species achieve it by adding radiation pressure that changes the speed at which the waves move. Modified recombination physics achieves it by shifting the moment the music stopped. Each approach targets the same physical quantity through a different mechanism. The sound horizon is the fulcrum on which the entire tension pivots. Others have explored whether the problem lies not in the physics of the early universe, but in the local environment. If our region of the universe happens to sit in a slight underdensity, a cosmic void, the local expansion rate would be slightly higher than the global average. This is called the local void hypothesis, and while it is physically plausible, the size and depth of void required to explain the full tension is larger than what most surveys of galaxy distribution support. It remains a possibility, but not a leading one. More exotic proposals exist at the fringes. Decaying dark matter, where dark matter particles slowly transform into radiation over cosmic time, changing the expansion history. Interacting dark energy, where dark energy and dark matter exchange energy in a way that alters the growth of structure. Sign-switching cosmological constants, where the vacuum energy of space transitions from a negative to a positive value at some point in cosmic history. Each of these has been explored in peer-reviewed literature. Each resolves some aspect of the tension while introducing new challenges elsewhere. The honest summary, as of early 2026, is this. No proposed solution to the Hubble tension has been accepted by the community as definitive. The field is not converging on a single explanation. It is diverging into an expanding landscape of possibilities, each one probing a different assumption of the standard model, each one revealing a different way that our understanding might be incomplete. This is not a sign of failure. It is a sign of how deep the problem runs. The Red H0T project, already discussed, reflects the depth of this uncertainty. When a major research institution funds a team whose sole purpose is to find flaws in the prevailing measurements and models, it signals that the field has moved beyond routine science into something closer to a diagnostic investigation. The standard tools are being re-examined because the standard answers are no longer satisfying. The Euclid mission, launched by the European Space Agency in 2023, is gathering data that will provide an independent map of cosmic structure and expansion history. Its primary results, expected in 2026, will offer a third perspective on the tension, distinct from both the distance ladder and the cosmic microwave background. If Euclid's measurements of baryon acoustic oscillations and weak gravitational lensing confirm the late universe expansion rate, the case for missing physics will strengthen further. If they show something unexpected, an intermediate value, an internal inconsistency, a new anomaly, the picture will grow more complex still. What has become clear is that the Hubble tension is no longer a dispute between two groups of astronomers. It is a structural problem embedded in the most successful cosmological model ever built. The model makes a prediction. The universe does not comply. The instruments have been checked and rechecked. The methods have been cross-validated. New and independent techniques keep arriving at the same conclusion. The late universe is expanding at a rate that the early universe, as interpreted through lambda CDM, does not predict. The uncomfortable possibility that the field now confronts is that lambda CDM, for all its triumphs, may be the wrong framework in which to interpret this particular question. Not wrong in the sense of being discarded, wrong in the sense of being incomplete. Like Newtonian mechanics, which works brilliantly for everyday physics, but breaks down at high speeds and strong gravitational fields, lambda CDM may be a limiting case of a more complete theory that we have not yet discovered. And there is one more dimension to this story that deserves attention before we pull back to the widest view. The Hubble tension is not alone. It is the loudest crack in the foundation, but it is not the only one. The Cepheid tension sits alongside it, pointing to a related but distinct mismatch between predicted and observed matter clustering. The unexpectedly massive early galaxies push against lambda CDM's structure formation timeline. DESI's hints of evolving dark energy challenge the cosmological constant itself. The Atacama Cosmology Telescope's measurements of the cosmic microwave background at smaller angular scales show subtle differences from Planck that remain under investigation. No single one of these anomalies is definitive. Each has caveats, each has alternative explanations, but the pattern they form collectively is harder to dismiss than any individual data point. Multiple independent observations, probing different aspects of the universe at different epochs and different scales, are all pushing in the same direction, away from lambda CDM, toward something else, something we have not yet identified. The history of physics offers a parallel. In the late 19th century, classical mechanics and electromagnetism were the twin pillars of physical theory. Both were spectacularly successful. Both had been validated by decades of experiment, and yet, at the edges, anomalies were accumulating. The orbit of Mercury did not quite match Newton's prediction. The speed of light appeared constant, regardless of the motion of the observer. The spectrum of radiation emitted by hot objects did not follow the expected curve. Each anomaly was small. Each could be individually waved away as a measurement problem or a minor theoretical wrinkle. Together, they were the warning signs of two revolutions: relativity and quantum mechanics. The anomalies accumulating in cosmology today are eerily similar in character, individually manageable, collectively unsettling, each one pointing to a gap between theory and observation that the current framework cannot close. Whether these cracks will lead to a comparable revolution is impossible to say. The answer depends on data that has not yet been collected and ideas that may not yet have been conceived. But the direction of travel is clear. The standard model of cosmology is under more pressure today than at any point since its establishment, and the James Webb Space Telescope, by confirming the measurements that create that pressure, has ensured that the field cannot look away. The instruments have spoken, the stars have been counted, the distances have been measured and cross-checked and measured again. The cosmic microwave background has been mapped to a precision that previous generations of astronomers would have considered miraculous. And when all of that extraordinary data is assembled and compared, the universe does not behave the way the model says it should. Not by a small amount, not within the margins, by a gap that the mathematics calls practically impossible to attribute to chance. What remains is the task of understanding what that gap means. Whether it points to a new form of energy in the early universe, a new behavior of dark energy in the late universe, a modification of gravity on the largest scales, or something entirely unanticipated, that task is not close to being finished. The measurements are ahead of the theory. The data is accumulating faster than explanations. And the most powerful observatories ever built are continuing to collect, continuing to refine, continuing to push the precision higher and the escape routes narrower. Whatever is hiding in the gap between 67 and 73, the net is closing around it. The question is whether our current theoretical imagination is large enough to recognize it when it is caught. There is a moment in the life of any scientific framework when the evidence stops fitting and the question shifts from how do we fix this measurement to what are we missing about reality. Cosmology has reached that moment. Not with a single dramatic failure, but with a slow accumulation of pressure from multiple directions, each one individually survivable, collectively impossible to ignore. The Hubble tension is the most prominent crack. It is not the only one. And when you step back far enough to see the full pattern, the picture that emerges is not one of a model that has failed. It is one of a model that may have reached the boundary of what it can explain. Lambda CDM deserves respect before it receives criticism. This is a framework that was assembled from a handful of ingredients and 6 adjustable numbers and proceeded to correctly describe the observable universe across 13.8 billion years of history. The cosmic microwave background, the large-scale distribution of galaxies, the abundances of light elements, the accelerating expansion, all of it predicted, all of it confirmed, all of it consistent to a degree that borders on astonishing. For 2 decades, every new dataset that arrived only strengthened the model. Every satellite that launched, every survey that was completed, every measurement that was refined, added another layer of confirmation. Lambda CDM did not become the standard model by accident. It earned the title through relentless confrontation with data, and it won. That history is what makes the current situation so significant. When a fragile model breaks, nobody is surprised. When the most robust framework in the history of cosmology starts showing cracks, the implications are profound. Not because the model is wrong in some general sense, it demonstrably is not. But because the cracks may be signaling that the model is a very good approximation of something deeper, and the approximation is beginning to show its edges, this is not unprecedented in physics. It has happened before, and each time it happened, the resolution reshaped our understanding of reality in ways that nobody anticipated. When Isaac Newton published his laws of motion and universal gravitation in 1687, he gave humanity the most powerful predictive framework it had ever possessed. Newtonian mechanics explained the orbits of planets, the trajectories of cannonballs, the tides of the ocean, the motion of the moon. It was precise, quantitative, and spectacularly successful for over 2 centuries. Engineers used it to build bridges and machines. Astronomers used it to predict eclipses and discover new planets. It was so successful that by the late 1800s, many physicists believed the fundamental laws of nature had been essentially discovered. All that remained was to fill in the details. Then the anomalies started accumulating. Mercury's orbit precessed at a rate that Newtonian gravity could not quite explain. The discrepancy was tiny, roughly 43 arcseconds per century, a measurement so small that it had been attributed for decades to observational error or the gravitational influence of an undiscovered planet. The speed of light turned out to be constant, regardless of the motion of the observer, a result that flatly contradicted Newtonian expectations. The spectrum of radiation emitted by heated objects followed a curve that classical physics could not reproduce without producing infinities. Each anomaly was small. Each could be individually set aside, but collectively, they were pointing toward something that Newtonian mechanics could not accommodate. The resolution came in two waves. Einstein's general relativity replaced Newton's gravity with a geometric theory of curved spacetime. Quantum mechanics replaced classical particle physics with a probabilistic framework operating at atomic scales. Together, they did not destroy Newtonian mechanics. They revealed it to be a limiting case, a brilliantly accurate approximation that works perfectly within a specific range of conditions and breaks down outside that range. The analogy to the current situation in cosmology is imperfect but instructive. Lambda CDM plays the role of Newtonian mechanics, spectacularly successful within its domain, confirmed by every test that falls within its range. And now showing deviations at the edges that resist explanation within the existing framework. The Hubble tension is not Mercury's orbit. The Cepheid tension is not the ultraviolet catastrophe. The situations are different in their details, but the structural pattern, a dominant framework encountering persistent small anomalies that multiply rather than resolve, carries a familiar shape. The question that the cosmological community now faces is whether these anomalies are pointing toward a modest revision of lambda CDM, something equivalent to adding a small correction term, or toward a more fundamental shift in understanding, something equivalent to the jump from Newton to Einstein. The honest answer is that nobody knows, and that uncertainty is itself a significant development. For 2 decades, cosmology operated with extraordinary confidence. The model worked, the data agreed, the parameters were pinned down. That era of comfortable precision is ending. What replaces it will be determined by the next generation of data and the theoretical imagination required to interpret it. The leading candidates for what might be missing fall into several broad categories. Each one touches a different assumption of the standard model. Each one, if confirmed, would alter our understanding of the universe in a different way. The first category modifies the early universe. This is where early dark energy lives. The idea that a brief injection of energy before recombination shrank the sound horizon and raised the predicted expansion rate. As we covered earlier, this approach shows promise but creates secondary tensions with matter clustering measurements. Researchers continue to refine the models, looking for versions that thread the needle between raising the Hubble constant and keeping the rest of the cosmic microwave background fit intact. A related idea involves modifying the physics of recombination itself. If the moment when atoms first formed happened slightly earlier than lambda CDM predicts, the sound horizon would shrink and the predicted Hubble constant would rise. One mechanism for achieving this involves a time-varying electron mass, where the fundamental properties of particles were slightly different in the early universe than they are today. This is speculative, but it is grounded in theoretical frameworks that allow fundamental constants to evolve over cosmic time. The constraints on such variation are tight, but not tight enough to rule it out entirely. The second category modifies the late universe. This is where evolving dark energy enters. If dark energy is not a cosmological constant, but a dynamic field that changes strength over time, the expansion history of the universe could differ from lambda CDM's prediction in ways that affect the relationship between early universe measurements and late universe observations. DESI's hints of dark energy evolution fall into this category. If confirmed by future data releases and by independent experiments like Euclid, dynamic dark energy would represent a fundamental departure from the simplest version of the standard model. The implications of evolving dark energy extend far beyond the Hubble tension. If the vacuum energy of space is not constant, it raises deep questions about the nature of space-time itself. In quantum field theory, the cosmological constant is related to the energy of the vacuum, the lowest energy state of empty space. A constant vacuum energy is already one of the most perplexing quantities in all of physics. The value predicted by quantum field theory is larger than the observed value by a factor of roughly 10 to the power of 120. This mismatch, called the cosmological constant problem, has been described as the worst prediction in the history of science. Making dark energy dynamic does not solve this problem. It transforms it into a different and potentially even more puzzling question. Why would the vacuum energy of space change over time? What physical mechanism drives the change? What does it mean for the ultimate fate of the universe? The third category goes further still. It modifies gravity itself. General relativity is the foundation on which all of cosmology is built. Every equation in lambda CDM rests on Einstein's description of how matter and energy curve spacetime. General relativity has been tested with extraordinary precision in the solar system, in binary pulsar systems, and in the detection of gravitational waves from merging black holes and neutron stars. In all of these regimes, it passes with flying colors. But cosmology operates in a regime where general relativity has never been tested to the same degree. The largest scales, the weakest gravitational fields, the most uniform distributions of matter. It is entirely possible that gravity behaves slightly differently in these conditions. Modified gravity theories explore this possibility. Some add additional fields to the gravitational sector. Some allow the gravitational constant to evolve over time. Some introduce screening mechanisms that make gravity look Einsteinian in dense environments like the solar system, while deviating on cosmological scales. The appeal of modified gravity is that it could in principle affect both the expansion rate and the growth of structure, addressing the Hubble tension and the Cepheid tension simultaneously. The challenge is that modified gravity models tend to be more complex than lambda CDM, with more free parameters and fewer clean predictions. The field has not yet produced a modified gravity model that resolves the tensions without introducing new problems. The fourth category is the most radical. It questions whether the universe is as simple as lambda CDM assumes. The standard model rests on the cosmological principle, the assumption that on sufficiently large scales, the universe is homogeneous and isotropic, the same everywhere, the same in every direction. This assumption has been supported by observations of the cosmic microwave background, which is extraordinarily uniform, and by galaxy surveys, which show a roughly even distribution on the largest scales. But roughly even is not perfectly even. And recent observations have raised questions about whether the universe might have large-scale structures or asymmetries that violate the cosmological principle at a level relevant to the Hubble tension. If our local region of the universe has a slightly different expansion rate than the global average, the discrepancy between local measurements and the cosmic microwave background prediction could be partly explained by cosmic variance, the natural statistical scatter expected in a universe that is nearly but not perfectly uniform. This is the local void hypothesis, and while earlier versions of it have been disfavored by galaxy surveys, more sophisticated analyses continue to explore whether local environmental effects could contribute to the tension. The contribution, if it exists, is unlikely to be large enough to explain the entire gap. But in a landscape where the full resolution may require multiple ingredients rather than a single dramatic fix, even partial contributions matter. What makes the current moment in cosmology so distinctive is that all of these categories are being pursued simultaneously by serious researchers with access to world-class data. This is not a situation where one speculative idea is competing against the establishment. It is a situation where the establishment itself, the teams that built and validated Lambda CDM, are the ones exploring modifications. Adam Riess, whose measurements created the tension, is also one of the scientists pushing hardest for the field to take the possibility of new physics seriously. Wendy Friedman, whose measurements are more conservative, nonetheless acknowledges that her data does not fully reach the Planck prediction. The Planck team itself has noted the tension in their published results and has called for new physics as a possible explanation. The field is not divided between defenders of the old model and revolutionaries trying to overturn it. It is united in the recognition that something is not right and divided only on what the resolution will look like. That is a healthy and productive state for science to be in. But it is also an uncomfortable one, because it means the most fundamental question about the universe, how fast it is expanding, does not currently have a settled answer. And from that unsettled answer, a cascade of other uncertainties flows. If the expansion rate is 73, rather than 67, the universe is slightly younger than Lambda CDM predicts. Not by enough to create a contradiction with the ages of the oldest stars, but by enough to change the timeline of cosmic history. The epoch of galaxy formation shifts. The period during which the first stars ignited shifts. The window during which the universe was reionized, when ultraviolet radiation from the first luminous objects stripped electrons from hydrogen atoms and made the cosmos transparent again, shifts. Each of these shifts is small in absolute terms, but in a field where precision is measured in fractions of a percent, small shifts propagate. If dark energy is not constant, the future of the universe changes. Lambda CDM, with a cosmological constant, predicts a universe that expands forever, gradually diluting all matter and energy into an increasingly cold and empty void. This fate, sometimes called the heat death, is the default prediction of the standard model. But if dark energy evolves, if it can strengthen or weaken over time, the far future becomes less certain. A dark energy that grows stronger could eventually tear apart galaxies, stars, planets, and atoms in a scenario called the Big Rip. A dark energy that weakens could allow gravity to eventually halt the expansion and pull everything back together. The fate of the universe, on the longest timescales imaginable, depends on the nature of dark energy, and we are only now beginning to gather the data needed to determine what that nature is. If gravity is modified on the largest scales, the implications extend beyond cosmology into fundamental physics. General relativity and quantum mechanics are already known to be incompatible at the deepest level. They cannot both be exactly right. The search for a theory of quantum gravity, a framework that unifies the two, has been one of the central quests of theoretical physics for nearly a century. If cosmological observations provide evidence that gravity deviates from general relativity on large scales, that evidence would be an invaluable clue for the quantum gravity program. It would not solve the problem, but it would narrow the search space enormously, ruling out classes of theories and highlighting others. The philosophical dimension of this story is as significant as the scientific one. For most of human history, the question of what the universe is made of and how it behaves was the province of religion and philosophy. The idea that we could measure the expansion rate of the cosmos to 1% precision, that we could map the temperature of the universe 380,000 years after its birth, that we could detect the gravitational influence of invisible matter that outweighs everything we can see by a factor of 5. These are achievements so extraordinary that they can numb us to their strangeness. We have built a model of the universe that works, a model that takes 6 numbers and from them derives the age, size, composition, geometry, and fate of everything that exists. And We have tested that model against observations spanning billions of light years and billions of years. The fact that it works as well as it does is one of the great intellectual achievements of our species. And now we are discovering that it does not work quite well enough, not because the observations are crude, because they are too precise. We have measured the universe so accurately that we can see the places where our best model does not fit. The cracks are not large. They are not catastrophic. They are the kind of subtle, persistent discrepancies that in the history of physics have preceded the deepest revisions of understanding. The James Webb Space Telescope did not cause this crisis. The crisis was already building when Webb launched. What Webb did was close the last escape route. The hope that better observations would dissolve the tension was the field's safety net. Webb removed it. By confirming the distance ladder measurements with its sharper, cleaner infrared vision, by verifying that the Cepheids were not contaminated, by demonstrating that the expansion rate measured from the nearby universe is robust, Webb forced the field to confront the possibility it had been deferring for a decade. The problem is not the data. The problem is the model. That word, problem, needs qualification. Lambda CDM is not broken in the way that a machine stops functioning. It is incomplete in the way that a map can be extraordinarily detailed and still miss a hidden river or an underground cavern. The map is useful. It guides you accurately across vast distances. But when you reach the point where the terrain does not match the contour lines, you know the map is not the territory. Something is there that the cartographer did not draw. What is there? That is the question that defines cosmology in the 2020s. The answer may come from the next release of DESI data, which will measure the expansion history with greater precision and test whether dark energy truly evolves. It may come from Euclid, which will map the distribution of matter across 10 billion light-years of cosmic history and provide an independent check on both the expansion rate and the growth of structure. It may come from the Vera Rubin Observatory, which will survey billions of galaxies and supernovae to unprecedented depth, building the most comprehensive census of the nearby universe ever assembled. It may come from gravitational wave observatories, which are beginning to develop techniques for measuring the Hubble constant through the detection of binary neutron-star mergers, a method that bypasses both the distance ladder and the cosmic microwave background entirely. Or it may come from an idea that no one has had yet, a theoretical insight that reframes the problem in a way that makes the tension dissolve not through better measurement, but through deeper understanding. The history of physics is rich with examples of problems that resisted solution for decades until someone asked a different question. The ultraviolet catastrophe was not solved by building a better thermometer. It was solved by Max Planck's radical proposal that energy comes in discrete packets. The constancy of the speed of light was not explained by finding an error in the interferometer. It was explained by Einstein's radical reimagining of space and time. The Hubble tension may ultimately be resolved not by a better telescope, but by a better theory. One that sees the universe through a framework we have not yet constructed. Until that framework arrives, the field lives with uncertainty. And there is something valuable in that uncertainty, something worth sitting with rather than rushing past. For 20 years, cosmology enjoyed a golden age of confirmation. Every observation matched the model. Every parameter was pinned down. The universe seemed understood in a way that previous generations could not have imagined. That confidence was earned. But confidence can also become complacency. A model that always works is a model that never challenges you to think harder. The Hubble tension is a challenge. It is an invitation to think harder. Not about whether the universe is real, not about whether physics works, but about whether the specific mathematical description we have built is the final word or merely the best approximation available with the physics we currently understand. The distinction matters. The first option means the cracks are errors to be patched. The second means the cracks are windows into something new. Adam Riess chose his words carefully when he described the situation. He said, "What remains is the real and exciting possibility that we have misunderstood the universe. Not that we have been wrong about everything, not that the model should be thrown away, that we have misunderstood. That our comprehension, as accurate and powerful as it is, has not yet reached the full truth. The universe is telling us something through the gap between 67 and 73. We have not yet learned the language well enough to translate it." The James Webb Space Telescope was built to see further and more clearly than any instrument before it. It was designed to answer questions. Instead, in one of the most important areas of modern physics, it sharpened a question that the field had been hoping would go away. It did not break cosmology. It held a mirror up to our understanding and showed us, with unprecedented clarity, the exact places where the reflection does not match what we expected to see. Those places are small. They are quiet. They are measured in kilometers per second per megaparsec, in sigma levels, in decimal points that most people would never notice, but they are real. They have been confirmed by multiple independent teams using multiple independent methods and the most powerful observatories ever constructed. They are not going away. And the history of science suggests that when persistent, precise anomalies refuse to disappear, they are not noise, they are signal. They are the universe trying to tell us something we do not yet understand. We are not at the end of this story. We are at the point where the old chapter is closing and the new one has not yet been written. The data is arriving, the theories are being tested, the telescopes are watching. Somewhere in the gap between what the infant universe predicts and what the adult universe reveals, there is a piece of the cosmic puzzle that we have not yet found. It may be a new form of energy. It may be a new behavior of gravity. It may be something so unexpected that it does not yet have a name. What we know for certain is this: the universe is expanding. The rate at which it expands has been measured with extraordinary care by the most capable instruments humanity has ever built. And the answer does not match the prediction of our most successful model. That mismatch is not a failure. It is an opening, a place where the known ends and the unknown begins. A boundary that James Webb did not create, but exposed with a precision that leaves no room for retreat. The deepest discoveries in physics have never come from the places where the model works perfectly. They have come from the places where it does not, from the tiny discrepancies that everyone else dismissed, from the stubborn data points that refuse to fall in line, from the moments when the universe quietly contradicted what we thought we knew and waited to see if we were paying attention. We are paying attention now. The cracks are small, but they are there. And behind them, something about the universe is waiting to be understood.